Okay, good afternoon, everyone. Today I will be talking about on-chip Raman spectroscopy and mainly the background challenges associated with that and how we can mitigate those. First off, what is Raman spectroscopy? It's a sensing technique that allows to probe molecular vibrations, like you can see here. And the idea is that an incoming pump photon has a tiny probability that it can inelastically scatter, meaning that it will change its frequency or its color as light. And this enables us to detect basically which molecule we are looking at. So in Raman scattering, we have two types of flavors, as you like. First off, you have Stokes Raman scattering, where the idea is that the pump photon will lose energy to a molecule and there will excite a higher order vibrational mode. You can also have anti-Stokes Raman scattering, that's on this side here, where the pump photon will increase its frequency, but at room temperature, Stokes Raman scattering is dominant, so that's what we were looking at in this work. And as you can see, those different peaks that you can see here, each of that corresponds to a different characteristic vibrational frequency of vibrational mode of the molecule. And very rudimentarily, we shine light on the molecule, and looking at the colors that come back from that, we can determine which molecule we are looking at, which is basically something that we have a fingerprint of the molecule that we can look at by looking at those characteristics. This is a phenomenon that was discovered by Raman, who is an Indian scientist. And the advantage of doing Raman spectroscopy is that it's non-invasive and label-free. You don't have to come in contact with the molecule, etc. And furthermore, you have these distinctive molecular fingerprints, which allows us to distinguish different analytes based on their characteristic peaks. Unfortunately, Raman spectroscopy is an inherently weak technique, and therefore it's really limited to the lab environment. And a typical Raman spectroscopic system in the lab looks something like this, where you have a laser right here, a confocal Raman microscope, where you have the pump light that's focused down onto a sample that you want to probe, and then the Raman scatter light is also collected and sent towards a deeply cooled detector. What can you do with this type of Raman spectroscopy? You can do non-destructive material analysis. For example, you can detect cancer cells. You can characterize 2D materials like graphene in this case for singularity, or you can also do pigment analysis for paintings, for example. But because you need all this costly and bulky equipment, we are basically limited there to the lab environment, and therefore we cannot take this technique on site. And therefore, recently you have these handheld Raman devices that have emerged that you can use on site. And you can do something like identifying different chemicals in a factory, for example, doing drug detection by the release, or do food quality monitoring. And although these devices are fast and you can use them on site, they also have a reduced performance compared to what's possible in the lab. Therefore, it's difficult to, for example, detect biomarkers in complex samples such as blood. And furthermore, they also still rather costly, still from tens of thousands of euros. And therefore, we can do on-chip Raman spectroscopy. And when I talk about chips, I talk about these chips that are in your smartphone or in the computers here or in your cars. And very simply, you could see this chip as a set of electronic circuits on a small flat piece of silicon. And the main building block on such a chip is a transistor, which is kind of a mini electrical current switch, which allows you to make logical functions on the chip. And the typical microchip has a couple of billions of those transistors. So therefore, to fabricate those, you need very advanced techniques, and the standard semiconductor technology is CMOS technology, which allows you to fabricate these chips with very high yields and also have very compact chips. And it's also a very mature technology because a lot of investment went into this area in the last few decades. And you can see, for example, here, a sort of device that you need to fabricate such chips. Those devices are very complex and also very costly, but we you can fabricate those chips in large volumes, and therefore in the end up with a chip that is at low cost, and meaning that you in the end can also have it all at your home and your devices. So with that, we also emerged into the world of nanotechnology, and just to give you an idea, a typical diameter of human hair is about 50,000 to 100,000 nanometers. So we're talking about 1 nanometer. It's just not just small, but it's very, very small. And how can we now use this to do Raman spectroscopy? We can use this technique to use the chips to fabricate this tiny light cables or light wires, as you want, which we call waveguides because they guide light waves. And the idea there is that you have a core material such as silicon nitride in our case, not silicon because it's transparent for the wavelengths that you want to use it, and you can have it in a strip waveguide, or you can have it in a slot where you have these two waveguide cores very close to each other. And when you have such a material and you surround it with a low refractive index material, you can confine your optical modes quite tightly. And what you can do with it is apply an analyte on top of this chip. So these waveguides are exposed to air. When you apply a droplet of a liquid on top of them, this optical mode that you can excite is not only inside of the core material, but also you have a field present at the surface, the luminescence field. And not only it's present, it's also enhanced, which actually means that the light that we can guide into these wires, this wires, actually comes in contact with the molecules of the analyte, and there it can again excite ground scattered light, and afterwards you can connect it. So you can couple in the light here at the beginning of the spiral, and then at the end you can couple it out and send it to the detector, and in it then you have these different Raman colors that you generate, which you can then use to tell which molecule is present on top of this waveguide. And besides this evanescent field enhancement, you can also have very long interaction lengths, way beyond the diffraction limit, because we insulate this optical modes to this waveguide structure, and therefore you can have waveguide lengths for about a couple of centimeters, which is an additional advantage of this technique. Here you see an example of a spectra that can be measured with it, and the abbreviation here, NWERS, means nanophotonic waveguide enhanced Raman spectroscopy. So we use this waveguide enhancement from Raman spectroscopy, and you can see in the spectrum here when we apply droplets to build alcohol. It's actually we can actually see those features popping up compared here and here and here, compared to when the droplet is not there. This actually means so we can do Raman scattering spectroscopy with it, and we can see when the droplet is not there. There's also a blue curve there, and this is due to the silicon nitride waveguide core, and this is actually the background that I talked about in the title. But more on the later. So the neat thing about this integrated Raman sensor is that you have actually a boosted Raman signal compared to what's possible with a confocal Raman microscope, like you have in the lab. So you have the improved performance, and furthermore you can detect monolayers, you can detect liquids, and you can detect gases. So there's a large variety in there. And furthermore, you also have the advantage, of course, that you fabricate this on a chip, and you can use these semiconductor technology, CMOS technology, which is already there for making electronic chips, electrical chips, and this enables us actually to fabricate complex photonic functionalities on a very compact chip, and we can also do it at a very low cost. So therefore, the idea is basically that instead of having all this equipment on the lab, we can actually all integrate that onto this tiny chip. And we can go from something that's quite bulky and costly to something that's much cheaper and also much smaller. I mostly work around this integrated Raman sensor here in my work, but you can also integrate your laser and detector or spectrometer onto such a chip. So On-chip Raman spectroscopy has the advantage of having a high performance. You have this boosted performance compared to free-space excitation and collection. And on the other hand, you can also take it out of the lab, you can use it on site, and therefore you can think about applications where you detect medically relevant molecules in complex environments such as blood or urine, etc. And basically the idea here is that you basically have your lab onto a small chip. And you can think about applications where you have dropped of your blood and you apply it on such a chip and plug it into a readout device. And then at your home or at the doctor's office, you can detect if you have a certain disease, for example, or you can also think about applications where you monitor the drug levels at the hospital. If they have to give you drugs to heal you from a certain disease, you can then detect at what concentration, for example, this drug is present and have this direct feedback loop. And you don't have to send everything to the lab anymore. Besides these bio applications, you can also do, for example, gas sensing, do environmental quality monitoring inside of your home, or you can also think about applications where you detect trace amounts of chemical warfare agents. And here I included an example. This is not Raman spectroscopy, but this is another technique with actinic sensing in this company called HANDHELD. Where the idea here is that you try to detect, for this certain application, detect SEs in urine, I believe. You apply a drop of urine on top of your chip device here, you plug it into this readout device, and you can also see the lab performance and the ease of use of something like a pregnancy test. You can do it at home, and you don't have to send it to the lab anymore, and you have a very reasonable price tag. Just in the following part, I will be talking about different types of Raman spectroscopy, and I will be using a lot of abbreviations. I already discussed NWERS here, but for example, just to give you a reminder, SERS is surface enhanced Raman spectroscopy, and then we also have SE-SRS, which is something we'll talk about, which is surface enhanced stimulated Raman spectroscopy, which is also more important, and then CTRs, where you have surface enhancement and then coherent surface. So again, coming back to this integrated Raman sensor where you have this long spiral waveguide, I showed you, okay, you can detect liquids. In that case, it has a boosted Raman signal compared to a conformal Raman microscope. But as you can see, there's also this blue background, which is, you can also see it here, with spectrum where the Raman are present, but this is our photon background. Which in the end will limit our detection sensitivity because it will become very hard to distinguish the background from the signal features, and therefore it will in the end make it more difficult to detect low concentration elements. And besides that, we also have the use of typical detectors, and those are costly, have quite a volume power consumption, and if you want to integrate those, you also have to challenging thermal management on the chip. So these are difficult to integrate, and we actually want to further boost this Raman signal because it's still quite weak on this integrated Raman sensor to levels that we no longer need this to be detected. So my colleague Ali Raza, he showed that if you perform SERS on a nanoplasmonic slot, where in this case you have these supernitride waveguide cores and the electric slot waveguide, you narrow down this gap, and inside the gap you have a very tiny layer of gold. And you can make use of plasmonic enhancements to really go to very high field densities inside this slot. And there the blue is then the analyte that's also present there, and therefore you can do Raman scattering again. But the neat thing about these sensors is that you can just generate an equivalent Raman signal to NWERS on the spirals, those centimeter long spirals. But you do so with a much more reduced interaction length. It's only a couple of micrometers. And therefore, the background to the plasmonic slot, the net effect of this reduced interaction length will be that you have a reduction by roughly an order of magnitude, which is of course good because it's a reduction in the photon backgrounds that I talked about in the previous slide. Of course, it generates equivalent Raman signals, so you will still need these typical detectors, but in the case of SE-SRS, you add coherent Raman scattering to this to also get rid of for the second problem, which is so although this sensor itself has a low background, of course, we also want to integrate it around scatter light, the Stokes light, and therefore you need these analyzing circuits where you, for example, have a bump projection filter or an AWG, which have a length of a couple of millimeters. So in practical experiments, what you do is actually you couple in the light here on the side of the chip and excite the mode there, and then the bump light will propagate towards the plasmonic slot, where the plasmonic mode will be excited, and then you collect the backscattered Raman light. But this excess or excess waveguide, depending if you talk about bump or Stokes laser, Stokes light, sorry, which in practical experiments make this very short. But if you have these analyzing circuits that we also want to integrate of a couple of millimeters, then actually the signal to background ratio will quickly deteriorate once you go into this length of a couple of millimeters. So you actually want to avoid the background contribution of that analyzing circuit and use the advantage that you actually have from the source sensor itself without afterwards still having a background contribution, which is due to this analyzing circuit. Therefore, in this work, I export this MMI-NANOPLASMONIC slot configuration. Again, here you have your source sensor, which corresponds to this part of the figure. And the idea is that you have the pump light, which is coupled into the input waveguide. Then you have the MMI, which operates as a 50-50 splitter. And then the lights coupled to the two arms of pump lights, where it will go towards the plasmonic sensor. And there we collect the backscattered Raman light, which will couple to this output port here. And here we can have a long output waveguide length. Because the neat thing here is that the bump light is forward propagating, and actually most of it will be absorbed in these plasmonic sensors, and only a tiny fraction of it will reflect back towards this output waveguide at the plasmonic slot interface, and therefore you can have an output waveguide which is quite long, but in that case doesn't really generate a very strong background penalty because the bump light that actually reaches there is very small. So then I had to experimentally verify this by first making these plasmonic sensors and coating them with NTP, and we can see the feature of NTP in this case right here. This is from my experimental measurements. And you can see you have a signal on one hand, but you also still have a background. So therefore, the second part of this work was basically to figure out where does the background come from. And in this case, I suspected that the excess waveguide and source sensor, they of course have a background, so that already part of that would explain the background that we observe here. So then I fabricated 4 different structures where 2 of them have a short excess waveguide length and 2 of them have a longer excess waveguide length. And you can see actually that the signal to background ratio deteriorates. So this already tells me that the excess waveguide plays an important role inside the background that I observe here. And then afterwards, I took the same structures and I cleaved off the output waveguide, going from output waveguide, which is 11 millimeters, to one that's 5 millimeters. And then I could see if the excess waveguide is short enough, then actually the background reduction to cleaving this output waveguide also is significant enough for me to detect it in the signal to background ratio. And from that, I could deduce that actually the background here is both to the excess waveguide and to the output waveguide. And both are roughly equivalent. While the MMI, or the input waveguide, if they really would have a strong contribution, then varying this excess waveguide or the output waveguide would have much effect on the signal to background ratio because they determine this background. So for this structure here, so you can see background comes from the 2 parts with a red circle around it. And I experimentally looked at the back reflection coming out, so the amount of bulb light that actually comes to the waveguide there. Could detect that with a detector, and I determined that it was around -27 dB. And from simulations, I showed that this back reflection is most likely from the slot here. But because this back reflection is not super big, actually I can also calculate that per unit length, the backgrounds to the output waveguide per unit length is about 173 times lower than the backgrounds to the excess waveguide, which is actually very neat because you can make this output waveguide quite long, 11 millimeters in this case, and in that case you actually still have only equivalent background as the source sensor itself. And finally, I also calculated signal to background ratio evolution with the output waveguide for our MMI case, which is shown here, and I compared that to alternative configurations such as the forward configuration, where the idea is that you simply have access waveguide, the source sensor, and then have the output waveguide behind the source sensor, and collect the forward scatter rather light. But in that case, the front light actually gets transmitted through this plasmonic structure and will still be present, and therefore it will generate, well, it will quickly deteriorate signal to background ratio of that configuration if you increase output waveguides. In the same way, you can also replace the MMI with a directional coupler, and then I also showed that, okay, the directional coupler, you know, they're smaller in length, they still give you converse signal to background ratio, and that's the effect that most of the background photons that you generate, the background photons that you generate in the MMI, are not efficiently collected at the output port because they don't couple in the correct power reflections to different guided modes in the MMI, and furthermore, they also need to have the correct phase because of the parametric process, meaning that in the end, most of the background photons are not efficiently collected in this waveguide. So in the future, one thing that can be done is fabricate the plasmonic slots with ALD gold instead of sputtering gold, which is to deposit the gold, the different techniques there. But sputtering has a more random nature, and therefore it's difficult in advance to know the amount of back reflection that you will get from this plasmonic slot interface, while you have better control, and therefore you have the better control about this plasmonic slot. You could also further engineer the MMI such that it acts as a wavelength division multiplexer, where the idea is that the front light is efficiently transmitted towards your source sensors, but afterwards it doesn't efficiently couple into this output port. And in this case, for example, you could set ports certain sensors on from each other, and then the ports one computers would be an antiphase. And that's one way you can achieve this wavelength division multiplexer. Or another way is another example I found in literature is using this angled MMI, where the front light gets efficiently transmitted towards the source sensor, but afterwards, by introducing this angle, you have these self-imaging points that differ for different wavelengths, and so the self-imaging points are then different spatial positions, and therefore the Stokes light can be efficiently collected in this case, but not the front light. And finally, you can also start thinking about combining the MMI with lattice filters, for example, rejection filters, and because you use the structure, actually introducing a structure with a couple of millimeters of length, such as a lattice filter, would not deteriorate the signal to background ratio too much in your structure. And then you combine the projection with those projection if you integrate on the waveguides both devices to further enable integration. Okay, so now I talked about how we can get rid of the photon background, use these plasmonic sensors, and how we can then use this MMI configuration to integrate it with analyzing circuits. But the second problem that we have is that we have technical detectors because the signal generation is quite weak. And therefore you can use coherent Raman scattering techniques such as two-wave Raman scattering or coherent Anti-Stokes Raman scattering, where the idea is that you actively drive the molecular vibration and you generate coherent Raman signals that will constructively interfere. And you basically can boost your Raman signal in that case, and you no longer only send in one laser, but you also send in a second laser, a Stokes laser, and by doing so, you actually increase the probability that Raman scattering will occur. In SRS, you try to detect the intensity increase on top of the Stokes laser, while in CARS, you try to detect this degenerated anti-Stokes frequency. And then Alan, who's part of the jury here today, he showed that if you SRS on the dielectric strip waveguide, then you can actually significantly boost the Raman signal compared to a spontaneous case, and this allows for room temperature detection. Coming at the cost of a more complex detection scheme with the lock-in, so quickly explain that. Because in SRS you need to detect the intensity increase on top of the Stokes laser, and in practice it's actually quite hard to do, because if you simply transmit Stokes laser to a chip, then actually the transmission variations will already be called according to the magnitude figure. The intensity increase because of the Raman phenomenon. But you can use a lock-in detection scheme where you modulate your pump laser, and then the Raman interaction, SRS interaction, will come on top of this source laser as a modulated signal. You can send that to a balanced detector to get rid of DC contribution, afterwards to a TIA for the amplified signal, and finally in a plug-in, which acts as a very narrow filter to filter out your RF signal, in this case of the SRS interaction. In this case, this is a more complex detection scheme, but you do get rid of your typical detectors, which are difficult to integrate. Because in this case, you also have the electric circuit guide that you use, which have a length of a couple of millimeters to a centimeter. You can have the issue that you have this photon background, and in this case, undetected DSO. There's the peaks here, but you also see there's still the presence of this photon background, and we know we can further reduce that by making use of this plasmonic slots. And that's what I explored in my thesis. So you can now combine plasmonic enhancement together with coherent Raman techniques. So in this case, I explored SE-SRS on the plasmonic slot waveguide, which again gives you a strong enhancement on one hand in the signal generation compared to certain plasmonic slots for NTP monolayer in this case. And this allows you room temperature detection. Okay, you have the block-in detection scheme, but on the other hand, with this technique, you also have good improvement in the signal to background ratio with about 2 orders of magnitude compared to SRS on the electric strobe waveguide, which further reduces the photon background, which is the additional advantage of using this technique compared to SRS. Of course, you can also think, okay, why not do CCARs? So I also calculated that in that case, with CCARs, you can also get a comparable performance to SE-SRS in terms of signal generation and signal to background ratio if you do it for NTP monolayer. And CCARs has a simpler detection because you need filters and a single pixel detector because it detects newly generated frequency. But in order to do it and get these comparable performance, you need a pulse pump laser. And therefore, in practice, it's actually you use much higher peak powers, which will lead to thermal damage to your plasmonic slot. And therefore, in practice, actually not so not so likely that you actually can achieve this comparable performance because you will most likely run into some thermal damage by using these pulse pump lasers. Furthermore, if you take this NTP monolayer and think about real applications such as detecting of biomolecules in the lab on a chip application, then I calculated what would happen if you decrease the concentration of this NTP monolayer by 3 orders of magnitude. And then you could quickly see that actually CCARs has a much reduced performance and signal generation, signal background ratio compared to SE-SRS, and this is mainly because of the fact that it has a quadratic dependency on concentration versus linear SE-SRS, and therefore actually signal generation goes up much more quickly when you go to low analytes concentrations or weak Raman scatterers, which is actually what we try to achieve. It's one of the applications that we try to achieve with such a sensor. So therefore, I explored SE-SRS in this work because of this sensitivity advantage that it has, and this is the setup that I use to do it. Not all details are important, but the idea is that, okay, you have a modulated pump laser, you send it out in free space and focus it down on the chip where it comes inside of the chip and goes towards this plasmonic slot sensor. And then you have the Stokes laser, and if the interaction goes as planned, you get this modulated increase on top of the Stokes laser to this SE-SRS interaction, and then you collect this SE-SRS light and send it towards your lock-in. In practice, this looks something like this here, where most of the equipment is not even shown. So these type of measurements are actually quite challenging to do in reality. But therefore, I first explored if the setup works as planned. So what I did was take an optical fiber and replace the chip and put a 6-meter long optical fiber, and then I could see that I actually could recreate the SRS spectrum that you also observe in lectures. So this already told me, okay, this setup works as intended. And afterwards, I moved towards measurements on a chip where you have a dielectric slot waveguide where I wanted to measure the background to the silicon nitride core. But in that case, I had to solve a couple of issues. First off, you have the fact that there are laser back reflections that occur when I focus down the Stokes light onto the chip tester. It back reflected and coupled back into the laser cavity where it causes instability, and therefore you cannot measure a good SRS spectrum. And furthermore, I also had to suppress the formation of cavities and stray light paths. So in order to understand this inside our chip, the Stokes light is propagating inside this waveguide mode, but at the facet, part of it can back reflect and actually couple back into the waveguide. And there you can form a Photonic cavity, a very weak one. In the same way, you can actually also have a formation of an anti-die because you couple light into the waveguide, but also part of it can couple into the cladding mode. And at the end of the chip, you actually can have interference between cladding mode and the waveguide mode. And that led to these fringe patterns that you can see here. Well, in order to understand why you can observe that, you have to look towards the nonlinear refractive index change that occurs by cross-phase modulation, because we know we have a modulated bump laser. So when the bump light is on, then we actually will have a different refractive index inside the cavity, for example, here, to when it's off, because you have this dependency on the bump intensity of the refractive index, and therefore you actually can change the transmission of your cavity for when the bump is on versus off, and that's actually something that leads to a transmission variation of the Stokes laser that's modulated and that you can pick up. In the same way, you can also have that in the waveguide mode, where the nonlinear refractive index change is felt in the waveguide, not in the cladding mode, because the light is not so tightly confined there. And therefore, when the bump light is on versus off, you'll actually have a difference in transmission that you can again pick up. And therefore, you need to suppress those effects. In case of the Photonic cavity, you need to dice your facets under an angle such that the waveguide light cannot back couple into the waveguide, but get reflected somewhere else. And in the same way, you have to put your chip under an angle during measurements to make sure that actually the cladding light and the waveguide light end up in different spatial positions, and you will not have this interference. Then you can see here that you will not get disturbed anymore by this various. So after all these things, I can actually measure SRS on an electric slot waveguide. And you can see here, you see the spectrum compared to the spontaneous one, and you see that it actually follows the trends quite. So then I knew, okay, with this setup that I have, I can do measurements on plasmonic slots, where the idea was to co-exist those plasmonic slots with the NTP signal, NTP analyze, such that again I wanted to detect these features on NTP. But instead of that, I actually observed, fortunately for me, something else. And it's basically those blue curves here, and you see, okay, they do not overlap, where those measurements are two types of gold deposition techniques, AOD gold and splitter gold, and I could measure that spurious spectrum in one case, and even when I didn't apply any analyte. So then I was thinking, okay, maybe again we have spurious SRS signal to do cross-phase modulation, or otherwise you also have to photon absorption. But transient absorption is something else which commonly been ensured using the spurious signal. But then I made a calculation for anti-die and Photonic cavity for free spectral range, and I can see actually that what I observe here doesn't overlap with that. And furthermore, if I did detailed measurements where I would expect these ranges to be, I also could not observe any ranges. And I also knew that I used the same chip to measure the spectrum of the dielectric slot waveguide, so I knew at least on that chip those effects should already be suppressed. And after a long time, actually figured out this background is to the thermal effect that's 2 orders of magnitude stronger than the Raman response. And it actually, as you can see from the figure as well, here we also have this red curve, and we can see that our blue curves have this overlap in spectral variation of the red curve, which is variation in the thermal extinction coefficient of gold. So basically, the absorption of gold changes when the temperature is also altered. So now to understand why this spurious effect occurs in the detection scheme, I already explained this part here. You want to see this modulating increase in the Stokes laser to the Raman interaction. But the same way, what also happens is that this modulated bump will get absorbed in the plasmonic slot. And there, after the temperature is in the steady state, you can see that there is still the presence of this thermal modulation inside of this plasmonic slot. And that's due to the modulated blood laser. And since we know that the extinction coefficient of gold depends on the temperature, this also leads to radiation and absorption loss felt by the Stokes laser propagating to it for when the bomb light is on versus off. And in the end, if the absorption loss changes, we'll also have changing radiation transmission of the Stokes laser. And you again have this modulated increase of the Stokes laser, but in this case, it's a spurious effect, which is 2 orders of magnitude bigger than the one to SE-SRS. So then I further had to confirm the thermal origin of this spurious SRS signal. And then what I did was actually increase the modulation frequency, and then I could see actually that the spurious signal actually has a clear line with the modulation frequency, which points to the fact that we're looking at a slow effect, such as the thermal effect, while those other effects like process modulation, photon absorption, transient absorption are considered faster electron effects in short line. Furthermore, I also made a calculation where I wanted to check how much of a temperature variation or modulation you need in the plasmonic slot for this background to be present at that strength. And I calculated that you only need a mild temperature increase in the plasmonic slot for this to be true. And furthermore, I also calculated that the effect to the thermal refractive coefficient is not relevant, because in this case you could also have the concavity as one, so then that you could pick off through the thermal variation effective index, but that effect I calculated was maybe smaller than that's to the thermal extinction coefficient. And finally, I also did thermal simulations to confirm this thermal modulation that I got from my calculation. So from these simulations, I got a number of about 5 kelvins in the side of the plasma slot thermal variation. So I knew, okay, it's quite realistic what I calculated here. So, and afterwards was also quite a neat thing where when I simulated this thermal variation in the plasmonic slot, and I changed the modulation frequency of my heat source in that case, I actually could recreate the bi-exponential effects that I also could get through my experimental variation of the spurious signal with the modulation frequency. And this actually points at the fact that there are 2 heat phenomena present in the gold, the faster heat flow of the gold compared to the surrounding electric materials. In order to show that, I placed several thermal monitors over the same distance inside of the silica, in this case, alongside the gold, which is, in my fabrication, I made it in gold sheets, so it extends about 6 micrometers each side of the plasmonic slot, and the same through the silicon nitride graphite core. And there you can see that actually the thermal response of this modulated temperature variation is stronger inside of the gold, the blue, compared to the surrounding electric materials, which actually is logical if you think about it, because gold has a low thermal resistance, and in this case, also a low thermal capacitance, because there's not so much gold present. And therefore, you can have, in case even if the heat source quickly changes from on to off, the temperature can follow fast enough in the gold, because you simply don't have a lot of atoms where you can distribute this thermal energy over. Therefore, you can still have this fast temperature increase in the gold, which makes a more effect, more broadband. And finally, also calculate the simulation where I did the equivalent of an impulse response, where I had a very short, the heat source was on for a very short time, and look at afterwards the time it takes to dissipate this temperature, and I can get constants that's much faster than the second one, which again can be attributed to the fact that you have a faster heat flow in gold compared to surrounding materials. So in the future, what can you now do to get around this spurious signal? You can increase the modulation frequencies to a couple of hundreds of megahertz to further suppress this SRS signal. You can also increase the heat capacity of the gold layer. Since we having more gold material, you can distribute the thermal energy over more atoms, and then in the end lower your thermal response, which is what you want. You don't want this temperature variation to happen more in the plasmonic slot, because that's what causes this change in absorption that's causing this spurious signal. You can also remove the thermal modulation altogether by the addition of a second cone laser, which is an antiphase to phase that's already present for our measurements, and you have to put it off resonance or wave measurements farther away. But then the result of that is that you get rid of this thermal modulation inside of the plasmonic slot to suppress the spurious. And then finally, a last word about the project that I worked around the first 2 years of my PhD, which was to probe acoustic vibrations of nanoparticles using these photonic integrated circuits, where the idea is that you apply a droplet of polystyrene nanoparticles in an aqueous solution. You can see them here at the top of the electric slot waveguide. And where you probe no longer the molecular vibrations, but the acoustic vibrations of the whole particle. And the idea there was that these plastic particles would be used as a proof of concept to later go towards detection of viruses, so towards an integrated virus sensor, and in this case, through a form of low frequency cars. And I estimated the signal that we should get out of this experiment should be 5 orders of magnitude above the nanoscale, but in practice I did not observe any signal. So therefore, we looked towards non-ideal particle behaviors. But afterwards, we refuted a long list of hypotheses, and I had to discontinue this project after 2 years because simply there were no results. So in conclusion, I showed in my PhD that you can use this MMI-NANOPLASMONIC slot configuration to allow to integrate the source sensor with an analyzing circuit without suffering from a large background penalty. You can use SE-SRS on the nanoplasmonic slots to tackle the problem of low signal generation of photon backgrounds, issues that you have with NWERS. Unfortunately, in practice, spurious background, there's a spurious background present in SE-SRS, which is of thermal origin, and this can be mitigated in the future. Measuring the acoustic vibrations of viral nanoparticles using photonic integrated circuits is challenging. Right, so that was it for me. Thanks for your attention.